All right, and we're back. Unfortunately, Brian actually can't be with us today. Got COVID yesterday, and he took the responsible thing and said, "Look, I'm not going to attend with COVID." So, but we've got more than enough on stage at the moment. So we're going to jump straight in. One of the ethos, I guess, of Pumps and Pipes is what's in the other person's toolkit. Okay. So Nick, what's in your toolkit?
Wow, we're just getting right at it, aren't we? Nice. Hi, Nick Radford, founder, CEO of Nauticus Robotics. Well, that's ironic because our major software platform that we run everything on at Nauticus is called Toolkit. And that's why our stock ticker is also KIT. It's actually more because I was a huge fan of Knight Rider, and I was like, if you can't have fun with your stock ticker, you're taking yourself too seriously. And I couldn't believe it was available actually on NASDAQ. But so we're wow. About 9 years ago, founded the company, and we took, I had about a 15-year background at NASA, deep in robotics, autonomous systems, and decided to take a lot of that technology underwater. And it's been a pretty heck of a time. But so the toolkit is comprised of, some of the latest and greatest in machine learning and technologies. Obviously, people, refer to that as sometimes artificial intelligence, but how do you interact with the world around you underwater, and do it in the context of very little data? So I'll try to see if I can get these slides to progress here real quick. It's not working. I'll start off with a little video.
Time immemorial, humanity has been fascinated with space. But perhaps we've spent so much time looking up that we've forgotten to look down. There beneath our noses lies the greatest hidden secrets and the key to our survival on this Earth. Our oceans are truly the last frontier on this planet. But that is changing. Over the past century, the best thinkers, dreamers, and makers have made gigantic strides to achieve the impossible in space. But what if those same people redirected their attention from the galaxies beyond to the depths below? What could we accomplish? What could we create? What could we do to save our planet? What if we could transform what is possible underneath the ocean waters? And what if instead of requiring this, we had this? With premier technology from some of NASA's greatest minds, determined to bring green solutions to an antiquated blue economy, we have created the Aquanaut, the first and only underwater autonomous robot, the deep sea pioneer, a transformer, a shapeshifter, and a catalyst that is modernizing the way we communicate, build, travel, and work in the blue. And we are only just getting started. Nauticus.
So that intros the company a little bit. So what did we do? We took about 20 folks from NASA. I don't get any Christmas cards anymore from the agency, but we started the company and have been really adapting the spaceflight tech to the ocean world. They're very similar problems, and it was a very natural segue. And so the ocean's just fantastic. It doesn't get a lot of, it's just not on everyone's mind, right? It's not top of mind, but it intersects every aspect of your daily life, from the food to the internet. 99% of data traveled around the world is on ocean cables. So it's enormously important, and especially the oil and gas industry, the exponentiating offshore renewable sector. And oh, by the way, it's 30% of the world's carbon dioxide is sunk into the ocean as well. So what we did was we took concepts in mobile manipulation, adapted them to common AUVs, and sorry, I'm just now seeing which slides are transitioning. So we took mobile manipulation concept in robotics, adapted it to common AUVs, and came up with the Aquanaut, which is essentially a subsea transformer. And we've been embarking on this pretty aggressive challenge. We're building a fleet of these machines. We have an autonomous surface vessel that drops off an autonomous robot. And we're essentially planting our flag in the blue economy and trying to completely change the way people use subsea robotics. So currently right now you basically take out an offshore service vessel. It's enormously expensive, puts out about 70 metric tons of CO2 per day, and has the world's longest extension cord. And so we've basically removed all that. And that's what we're doing. So Nauticus is well positioned to essentially be a 21st country for, 21st century company for I would say it's going to be one of the epicenters of these industries in the future, which is the ocean economy.
Wow. How much is a robot?
How much is it?
Yeah.
Well, the robot itself is about 4 million or so.
Okay.
The boat's about 3 or 4, depending on how bad the pound is cratering against the dollar, because we build all our ships in the UK. But the business case is for a $7 million capital expense, we make $8 million a year over about 8 years of its depreciable life. So it's a decent business case.
Superb. And Dr. Lumsden, switch over to medical. What's in your toolkit?
Well, depends who we're talking to. If we're talking to Nicholas, then we're talking about imaging and robotics and navigation. He said autonomous robotics. And so autonomous means you've got a plan. You can pre-flight the robot. We are very interested in that. We take it from the point of view of we created what we called MIRRAN, the Methodist Institute for Robotics, Imaging and Navigation. Our concept is that imaging is fundamentally important to us. And it's like the universe. It's like a map of your universe. And if we can integrate the plan for the robot into the pre-existing imaging, then that will take robotics to a whole nother level. So as you're talking about this and thinking about it, we want to know how you make these autonomous. Do you basically start off with a map? What is that map? And then how do you impute that into the robot so that you can control it? Let me go back a little bit, because we've been doing this now for about 15 years, and I really want to give the front table here some credit and get them to stand up. Bill Klein, one of the founders, stand up. Steve Eigel, stand up. And Rustam has been involved in this since day one. And so let's talk about, how did this come to be? It came to be because in the cardiovascular surgery world that I live in, there's a thing called a greenfield filter. Okay, nobody needs to know. Greenfield was a surgeon, and he was a surgeon at the University of Michigan. And he was having dinner with his next door neighbor, who kind of said, and I'm paraphrasing obviously, "How was your day, Laser?" He said, "Well, my day really kind of sucked." And he said, "Well, what was so bad?" He said, "Well, because there's a young man came in a motor vehicle accident 48 hours ago. We operated on him, we saved his life. Today he dropped dead from what's called a pulmonary embolism, a blood clot that formed in his leg, traveled through the circulation in his lungs, and essentially blocks the cardiac output." So his next door neighbor said, "So how does that happen?" He said, "Well, the basics are there's 2 tubes in your leg. They join to make 1 tube that goes to your heart. And once you block something like that off, there's no circulation." And so his next door neighbor said, "Well, why don't you put a filter in that tube coming out of the legs?" He said, "Well, nobody's ever put a filter in a blood vessel." He said, "Well, in the oil and gas business, that's what we do. We put filters in pipelines." And the dumb surgeon said, "So kind of like a sieve?" I said, "No, you can't put a sieve in a pipeline. You block the whole pipeline off. You've got to exploit the fact there's laminar flow. Center line has the fastest velocity. That's where particles travel. And you want center line, filtration is what you got to do." And that led to the development of the first ever inferior cable filter called the Greenfield filter. But the story didn't end there. What you had was the physician who identified the problem. The engineer is a smart guy, which is kind of why we want to surround ourselves with engineers who solve the problem. But then they linked up with a guy called John Abele. And John Abele was the founder of Boston Scientific, which is probably the 3rd largest medical device business in the world. All these medical device companies started in somebody's garage with someone who had an idea. And so again, it was that triumvirate of the physician who identified the problem, the engineer who solved the problem, and the business guy who took a great idea and converted it into something that's commercially viable. So that's kind of where the idea kind of came from. And then fast forward, this is why, being able to meet in person is so important, be able to open up our institutions to engineers to come visit. Because fast forward, Bill brought a group of ExxonMobil engineers to Methodist. And, one of our partners, Steve Little, had this really little closed circuit with a pump. That pump was what's called a left ventricular assist device. Your heart fails, you put a mechanical pump in, it augments the pressure. And that was hooked up to a circuit, and it made water flow through the circuit. And in it, we had a little box where you could put heart valves. And the pump had pulsatile flow, just like your pulse. And the heart valve would open and close. And we could study that using ultrasound. And Bill's group said, so what are your challenges? I said, well, we're really interested in MRI. Now, we can't put this big hunk of metal inside an MRI scanner to use it to study what's going on. And Bill's group said, we got it. And so they came back and made the only MRI-compatible flow loop that you could control, for example, the pressure volume curves in your left ventricle, impute that into the software that they created, and allow us to study that. And that led to multiple different grants and advances that occurred. And so we were very grateful to Bill until he decided, well, it's about quid pro quo. Here's what we really need. We want to study, it's called a gravel pack, the completion well bore. We want to study what the hydraulics are of a completion well bore. And that led them to bring down this gigantic plastic thing that they made up that mocks up how they complete a well bore, because they wanted to minimize turbulence. Turbulence equals energy loss is less production. And they put that inside an MRI scanner, a brand new MRI scanner I would add, and pumped ungodly amounts of volume through this. And I thought, oh, this is going to be bad. The first pumps and pipes product will be, I'm going to get fired because they destroy our MRI scanner. But that was subsequently published in the World Petroleum Journal. And that's an example of, there's a lot of things that we did not impress them with. The one thing we did impress them with, and my partner Bill Zogby is responsible for a lot of that, is the quality of the kind of imaging that we're using. I think it can be applied in a variety of different circumstances. So I could kind of go on and on and on. Metal fatigue, stents that you put in blood vessels break. And so amongst the world's experts, are in the oil and gas business. Infection, we put heart valves in, they get infected. There's not a device you can put in a human that cannot get infected. Once it's infected, it's coming out, and sometimes that's a big and dangerous operation. So not a single physician that I know of knows that pipelines get infected, and that microbial-induced pipeline corrosion is a $billion-a-year problem because of bugs which grow in pipeline. And it's another area basically we've been talking about. So what we've always been looking for is, and one of the earlier pumps and pipes was, I paraphrase the other guy's toolkit. As physicians, we by and large, even though we're going to different specialties, train in 99% the same way. To get these big breakthroughs, we need to work with people who work in a and potentially scalable problem, but are not constrained by what we've been told can be done or cannot be done. And that's the beauty of a meeting such as this, is to be able to talk to other people. So we got lots of toolkits. I think you're going to go on and talk about VR and simulation, and we'll come back and really talk about this a little bit.
Yeah, I think that's a good segue onto this video. Part of Mariner Robotics Institute, we're doing a lot of extended reality work, using it for robotics. So we have two things in our toolkit at the moment that we're pioneering.
At Houston Methodist, we are creating new realities for our patients, staff, and the global health community. Viewing the whole patient at a time. Exploring the heart from the inside out. Hands-on practice when you need it the most. Remote assistance for times of urgency. And if we are limited by our reality, we create a new one. Welcome to the Mightyverse.
Dr. Lumsden is here wearing a HoloLens, and he's in a hybrid OR. And what's happening, Dr. Lumsden? What are you doing here?
So when you use the HoloLens, it looks like I'm trying to do my own magic show there and failing dismally. But this is actually what you see through the HoloLens. This is a control system for a catheter robot. And the whole idea of this is that, the catheter robots, the whole idea of that was to get the operator out of the radiation field. And what this has been doing is to actually get you completely out of the building. And so that by wearing a HoloLens, you can actually control these robotic arms, which then manipulate the catheters. And the big application for this is potentially in stroke therapy. Stroke, it's multiple clinical trials have clearly showed that the way you treat thrombotic, which is a piece of a clot goes on up in your brain, is for somebody to put a catheter up there and take it out. Now, if you live in Houston, multiple institutions can provide this service. But as Bill Klein kind of pointed out, you don't have to go very far away from Houston. That service is not available. And so one of the things that's being looked at is could our stroke team work remotely, put these robots in a variety of different hospitals, and then potentially remove the clot. And this is just another way in which this could be applied.
And just really quickly, so both those things you saw are here for demo today. The Mightyverse has a demo station, so go in it and you'll be patching with people in the UK. Fundamental VR, they're in the UK right now, so you can go in and speak to them and like see a patient's heart in your hand. The second one, the robotic controller, was made by Titronics, and they're also here today, so please go and see them at the exhibitor booth. Jimmy, over to you though. What's in your toolkit?
Well, let's talk about it actually. Stuart, thank you so much for the invitation to speak to this audience here. So as I was introduced, I'm part of the Translational Research Institute for Space Health, or TRISH for short, and also part of Baylor College of Medicine. And we're looking at how our institute is a innovative biomedical research institute, and we look at how to keep humans healthy in space and also performing at a high level. So this includes both professional astronauts that are government sponsored, as well as now the private commercial sector, which if you've been following the news, we've had some recent private astronauts that have gone to space in the last year. And so we count those folks as parties that we're also interested in keeping healthy. And so what we do at TRISH is we actually are a cooperative agreement with NASA's Human Research Program, so we work hand in hand with how NASA wants to keep their astronauts healthy in spaceflight. However, our approach, because we're an innovation institute, is to take bigger leaps, take more disruptive approaches, be much more risk tolerant with how we address the hazards of spaceflight. And so I'm gonna kind of put a picture up here. My one slide that hopefully will come up soon. There it is. Okay. So if you guys are not familiar with this photo, this is taken by the Mars Curiosity rover from the surface of Mars. This was taken in 2017. And I don't know how well you can see it because I'm kind of looking at the screen here, but that's Earth. Earth is 4 pixels. So all of human history, all of human culture, all of human infrastructure is now on this picture, the size of 4 pixels. So when Stuart asked me what toolkit that I'm working on, I chuckle because I don't have a toolkit. I have nothing on the surface of Mars. I have no infrastructure, I have no human resource, and I have no capability that we here on the planet Earth have our 25,000 years of civilization have finally built up. And so the challenge I have is how do I now do that in the next 20, 30 years that we always keep talking about Mars is 20, 30 years away. How do we do that? And so what I'm really encouraged about is the companies here, especially in the Houston area, that are working on bits and pieces of that toolkit that we're trying to put together. And the challenges that we have are that not only is the distance great between Earth and Mars, but the time latency is also great, right? It's more than just, hey, it just takes a while to get everything I need on my rocket that I've taken to Mars. But if I actually needed to call back to Earth and get subject matter expertise on Earth and all of Earth's resources to bear to bring forward a challenge, to solve a problem, I now have to deal with a comm delay. And so it's both of those challenges together that is really difficult. And so because of that, we do focus very heavily on automation. But the challenge is how do we now provide the medical automation, the medical expertise, not just how we process information being collected off of the sensors and the medical devices that we have on the vehicle, but then turn that into information and then actionable instructions for the crew that's at hand to be able to do the task and then appropriately train them. Because keep in mind, these are professional astronauts. They're training to survive on an austere environment like the moon or Mars. They're not going to be fully trained physicians, clinicians that have their skills and up to speed and everything like that. So for us, it's not just a logistics and resupply challenge, it's also a cognitive knowledge issue as well. And so it's the approach we're trying to take in the toolkit that we're trying to work on Trish is instead of worrying about taking everything with us, let's take advantage of the speed of light. And so my approach that we're focused on is basically digitalization of our toolkit to go into space. So 3D printing, instead of taking the materials you need already created, you fabricate it as needed, right? Now I know you got to deal with the feedstock issue and things like that, and so hopefully there's going to be some breakthroughs there to help deal with that problem. Second is now technologies such as AR, XR, MR with AI, being able to present rich content to be able to train and keep skills up to speed so that the actual hands that are next to the patient know what to do and when to do it and how to do it. And so, it's not any specific toolkit that we're developing, but a broad kind of a all-encompassing set of toolkits we're looking at. And so it's really interesting for us to see companies innovate here to solve specific problems here on Earth. Because I guess an opportunity here is like, why would you be interested in space? Well, I would say you should be interested because there's still a human involved, right? So human problems will still exist in space. And so if you can solve and use space as a forcing function for solving the issues we see in space, there is actually could be a business case on Earth as well, because it'll be the exact same problems because you still have the human system involved. Thank you.
Yeah, I mean, that's a very good point. It seems in all three of your sectors, you're at some point you're faced with doing things at a distance. There's this latency. You want something to happen based on real-time data. So Nick, can you tell us a little bit more about your technology? How the robots go underwater, how do you communicate? How do you deal with latency?
Sure, and actually I think it's a good way to bring some of these concepts full circle, because the robotics lab at NASA that I was really fortunate enough to work in for like 14 years of my life, one of our applications was telesurgery. We had a very dexterous bimanual and a very dexterous end effector hand that surgeons would come in and they would actually practice doing telesurgery, or we developed some of the concepts of doing telesurgery. Well, as soon as you're traveling around, let's say we're operating in Houston and we want to do something, on the other side of the world, you're dealing with significant latency. So we were developing technologies and techniques to handle that latency, predictive displays, where's my robot going to be, just all sorts of concepts. So it turns out the robotics that I'm in now is underwater, and very similar challenges with latency. Spaceflight communication is pretty bad too. There's a significant amount of latency even to the space station, frankly. And underwater, similarly, the speed of sound through water is about 1,500 meters per second. We use acoustic modems to communicate with our robot underwater. And so you can imagine, let's say you're 3,000 or 4,000 meters away, small slant angle vertical channel communicating to your robot underwater. You're dealing with 6-second round trip latencies. Not only that, but you also have bandwidths that are akin to dial-up networking like 1987. And so we actually derived a lot of ways of handling that out of spaceflight. For example, disruptive tolerant networking, which is a deep space communications network. We're applying that overlay to our acoustic modems that we use to communicate with the robot. And actually, in our toolkit software stack, the application is called Wavelink. And so this is an example where we were informed tremendously from what we were doing in spaceflight and applied it to the ocean space. And there's the analogies don't stop there, frankly, but they're tremendous.
So let me join and ask you some questions. Again, blood is opaque. We can't see through blood. Space is transparent, and I guess the ocean most of the time is transparent. What are the sensors that you're using to navigate these robots? Do they see? Is it radar? Is it GPS? What's the secret sauce that's in there?
Yeah, well, unfortunately, all RF communication except for the ultra low frequency is absorbed into the water pretty quickly. So you can't communicate with radio frequency only but just a very short distance or extremely long wavelengths, right? So it knocks out all that sort of stuff. So sonar is a big deal, right? We have 3D sonar. Obviously, the modems are sonar related. They're acoustic. Light works, right? So we have a lot of visible cameras, different spectrums of light as well. So we use lasers to do ranging. But basically we developed this 3D environmental picture that's a combination, a fused combination of sensors across all different spectrums. And we fuse that into one composite image. We run it through a machine learning compression algorithm and send it out over an acoustic network, and it's reconstructed at the UI of the operator. Exactly the same way we were doing it at NASA as well. Just, exchange this sensor for that, put some salt water instead of space, and very similar concepts.
And so what are these things doing down there?
They're mainly just hanging out and sort of playing cards and stuff like that. But no, there's just an incredible amount of industry underwater that doesn't get a lot. So this has become an obsession, maybe a passion. Obsession is a bad word. No, it's an obsession. So coming out of space flight, there's so much attention paid on space flight, right? It's this existential, let's go off into the final frontier, XYZ, we can look up, everybody's got sort of this relation to feeling, but the ocean is so much more relevant to us now. And so if you look at the disparities of research dollars that go into the outer space versus ocean space, it's about 100 to 1. And this is a $2.5 trillion economy that touches every aspect of your life, like I mentioned earlier. Whether it's the energy we get out of it, the charge you're putting in your car, the food that you're eating, the data that you're getting on your phone, the goods that you're all wearing probably were shipped across a container ship, right? And yet it's never top of mind for anybody. Maybe outside of, maybe inside of Houston a little bit more because of the offshore industry, but you get outside of here and no one pays it much mind. So part of Nauticus's ambition and goal is to bring a much higher awareness to the ocean economy, making that connection to space flight, because people are very inspired by being in space, and so we want to draw some of that inspiration and shine a brighter light to the changing blue economy, which is going to support everything from the energy transition to the new food sources. If we continue overfishing the world's oceans at the same rate we are right now, we'll deplete the usable stores of fish in 40 years. And nobody talks about that, but it's a huge problem. As a consequence, aquaculture is exponentiating, right? So we're attacking this industry, drawing in the space tech to something that I think is extremely apropos near term.
Can I ask Jimmy a question?
You want to, maybe get from a space angle as well. We're going from oceans, from Earth into space. So how do you guys, how do you deal with latency up in space, and especially with things like medical interventions, like real-time action items?
Yeah, fortunately, we have not had to, knock on wood, had any major medical events in spaceflight. And also, our culture hasn't made it beyond low Earth orbit, at least other than the Apollo missions. Now, I know we're heavily focused on Artemis. I hope you guys are following the journey of Artemis 1, as it actually right now is flying by the moon. But yeah, for the most part, from a human presence perspective, we have not had to deal with the latency too much. Despite what Nick said about the communication latency with space station, surprisingly, despite only being about the distance from Houston to Dallas upwards, there's actually a 2 to 3 second communications delay, and it's mostly due to how signals work through our ground relays and things like that in our satellites. So even with that little bit of latency, we can still tolerate being able to do real-time communication with between mission control and the astronauts. However, when we look at the moon, right now the Artemis program is planning around about 7 to 8 second latency. And so it becomes a little bit more challenging in terms of a four-fold latency going on. To be frank, we don't really know what's going to happen to medical care. We haven't done it before. We haven't done a whole lot of it before to really understand when push comes to shove and you're talking about an operator that is working, trying to treat a patient on that is not up to speed on medical capabilities, their training, their skills may not be refreshed. What would happen? What would happen with the data that's being collected? Who makes decisions? Is it the person that is next to the patient, or does someone in mission control do it? Like these sort of this sort of model, this sort of paradigm hasn't really been tested, and so that's actually a focus on the Trish side. Is not necessarily, we obviously need to build the toolkits to be able to start doing it, but we also need to start creating the simulation environments and the analogs that we can start putting hundreds of thousands of people through to figure out, okay, is this better than what we've already been doing? So there's still a lot of research, just even is the model better? So I'm going to cheat a little bit. I don't have a direct answer to you, Stuart, but I think the reality is we just haven't gotten there yet, and we're looking to find partners that can help enable that.
Yeah, I think this goes on to our kind of last question here about the use of extended reality in your day-to-day operations. You know, people are using VR headsets to access Web3 applications. You heard earlier, for example. But how is XR, like extended reality, being utilized in your day-to-day operations?
So I think that's a technology that's now slowly being adopted, and I think kind of like what I was saying earlier with my previous comments, I think it's there are a lot of groups that are just looking how to better enable it. You know, in many ways, a lot of this tech is nascent, and its application, there's still folks just figuring out how to best develop content for it. Where our approach has been to, again, not necessarily focus on the content and the widgets, but how can we utilize it to better streamline communications, pushing of knowledge and information from expertise to someone that's next to the patient to be actually do it, right? Whether it's human hands or robotic hands, you know, doesn't really matter as long as we're able to actually affect the person who's injured. So approaches that we're looking at is taking advantage of, for example, the remote assistance capability of being able to have the expertise be situationally aware, and then provide some annotation with digital assets that the operator can see and go, okay, I put the scalpel here, or I know to look for the pulse here. You know, I may not necessarily be medically or clinically trained, but if someone told me how to do that and gave me an arrow that said, do that here, I might be able to do that. Now, again, that is dependent on some level of real-time communication. And so, again, we were trying to figure out how to best model that for low Earth orbit and lunar operations. But the hope, you know, is, you know, this is the grand vision, is at some point, that human expertise that's on the other end of that AR, MR platform slowly becomes artificial intelligence. Slowly becomes that doctor in a box, holographic doctor that I see on Star Trek. That's the slow hope. And again, obviously, there's a whole bunch of stacks, technology stacks that need to be put together to get there. But that's the vision, is we're just trying to get there in the foundation, start proving the concept of can you start offloading expertise, medical expertise off the human, start putting it either into the humans that are local to the patient or into an algorithm, artificial intelligence, that can also then supplement and support.
Yeah, so I think everybody's asking that question at the moment. Again, it's worthwhile. VR is where you're completely inside the domain. Show of hands. How many people have actually had an Oculus Quest on their head and utilized it? Yeah, quite a few. So that's true virtual reality. You're completely immersed. Now, there's a little program called The Plank. If you want to see how it viscerally affects you, go get the plank. You go up an elevator door open, and there's a plank sticking off the 61st floor of a skyscraper. Now, you know you're in your kitchen. You know you can't get hurt, and you're supposed to walk that plank. It is very challenging. Some people will refuse to do it. So we know that these things can bring a sense of reality, more than reality. What I was wearing was the HoloLens, where it's more like a fighter pilot. You can see in the environment. So as a surgeon, you would be able to see, but you can actually bring in reality. So for example, we could bring in the CAT scan of the patient who's laying on the table and make realistic decisions of where we're going to make an incision. And that's the sort of thing that can actually be utilized for. The problem at the moment is that, you know, those headsets, the ergonomics of those headsets are not great. For procedural training, where you're going to be in it for 20, 30 minutes, not a problem. For bringing in a symposium like this, it ain't going to happen, you know, with what we've got at the moment. So I think it's right. There are companies who will build procedure training into this. It is very realistic. And it's the sort of thing that we're trying to explore more and more and more. In the surgical world, the criticism has been lack of haptic feedback. And I think fundamental surgery, the group that we're working with, they have focused on being able to introduce haptic feedback so that you can, as a surgeon, for example, you can actually feel a little bit of what you're doing.
Nick, last comment from yourself, sir?
Yeah, so our entire thesis is exactly this, that the old way of doing work in the underwater industries made usage of operators with joysticks looking at video screens. And what we've decided to do is to embed a significant amount of self-directed and self-sufficient behaviors of the robot, and we fly the autopilot of the robot around with a mouse. But the operator is consuming data which is essentially mixed between still imagery, updated multispectral feeds, and there's this mixed reality of what they're seeing, overlaying models of subsea infrastructure that we know are there, and then having the robot handle some of the real-time requirements of, say, marine growth. And so we have this very rich mixed environment that is presented to the operator. And so it's, I mean, it's directly applicable in all the advances that are being made toward this. Because the only way that you can handle some of the latent challenges we were talking about is through this very judicious usage of the intent of the operator, where we think the robot's going to be, and that feedback loop. And so we use it extensively.
Okay, well, I think...
Can I make one more comment?
Yeah,
so,
of course.
I had the opportunity one time to go to Trondheim in Norway, which is kind of where NTNU is. It's the big petroleum engineering university in Norway. And they had built an offshore technology command and control center, but the platforms that they were running had all been scaled up in virtual reality. They did the safety training in VR. Okay, I mean, I don't know enough about it, but there's a fire over here on the left. What's the nearest escape route? Where are the fire extinguishers? And all of that was rehearsed in VR before the guys kind of went offshore. And they were doing kind of what you said, is that they had these massive data streams that were coming in from all over the place. And they weren't allowed to turn the valves. The guys on the platform didn't give them that kind of command and control, but they were advising continuously about the state of the platform. And all of that was done basically with a command and control center, onshore. And what you're really talking about, and we don't do this very well, is taking all of these different data sources around our patient, for example, or around their heart and their function, and pulling it in. We kind of have to individually kind of go look at and pull out each one of these different things. And how you do that is one of the things that we could learn from.
Okay, well, I think on that note, thank you all for listening, and thank you, gents, for on the panel. Okay, thank you.